Okay, let us begin the class. Today marked the end of our 4th week. So next week we will have the exam 1. Yeah, I have stated in the announcement 25th September, which is Wednesday. Okay, as you wish, yeah, Wednesday, right? Not Monday. We will do it in 7th floor, room 1. That's next to the IoT lab. Do you know? Computer lab. Yes. I want to use this time because I know that Fahri is having another class on 16, right? So we want to finish before that. You will have 2 hours. There are 4 problems, and the topics of each problem I have stated in the announcement. You see the announcement?
Yes.
So you can learn based on the topics. Any question about the examination? Is it open book or closed book? You don't want to know? You are cheating then.
Okay.
Intentionally.
Ilegal nggak cheating? Obat notes.
You can use Laplace table and the block diagram. Yeah, algebra. Yes, not necessary. It's optional. You can bring that, or you don't want to use. You can don't bring anything. Also can. Yeah. No.
Bawa juga bang.
And you cannot use smartphone. So please bring your calculator. Bring calculator. Cannot use. All the more cannot use. So bring your own calculator. Yeah. Don't have calculator? Buy today. Yes. Yeah. Graphic calculator. Yeah. But you will only use the plus minus. It's okay. Okay. And then what else? No. You have to remember that. Yeah. The topic is there already, right? I have mentioned the topic, so you have to remember all of them. If you want to use cheat sheet, then I will not give the topic. You understand? Yeah, you will not know the topic, but you will be allowed to use the cheat sheet. It has to be fair. Okay, in week 4, which is today, the emphasis is the second part. Yeah, computing the appropriate controller for certain requirements. And before we go into that, I want to explain the result on spacing control of car. Last week, I told you that we can create a control system in Simulink for the spacing control. Okay, you still remember this? This is the displacement and this is the torque. Okay, and then we don't give any disturbance here, but we only want the car to has a desired distance. Yeah, there is a desired distance between our car and the lead car. Yeah, and then these are the block diagram that we created. So the displacement from the lead car is measured by using radar or infrared sensors. There you go, you have the measured distance, and then this measured distance fed back into the controller. You get the error, and then the controller process that into the torque. Does it work? Yes or no? What do you think? Yes. Uh, any logical reason why this will work? Yeah, before you test anything, any logical reason if this will work? The torque controlled by the error. What else? What else? Sorry. Yes. What else? Same unit, yes, that one. Mm. So basically, if you build the control system and the control system is stable, okay, and if the controller is correct, yeah, let's say you have to use at least integral control, not proportional control, to reduce the error, to make the error to be zero. If that's correct, then actually this formulation is going to make the error smaller and smaller. Okay, so this step over here is actually trying to make the error to be smaller, because the torque here is the error multiplied by something, or you integrate the error, or you differentiate the error. Okay, that kind of mechanism is going to make the error smaller and smaller if the whole system is stable. That's the whole point. Yeah, so this is the Simulink block diagram which I created. You see, this is the plant, the ego car, and then the lead car is over here. Yeah, so you see, the lead car is independent from any kind of system. Yeah, so we just give an input to the lead car, and then the lead car will just move on its own, and then we want the ego car to follow it with a certain distance. So we have a subtract here, and then fed back. There are two lines. What are these two lines? Do you know? The feedback line is only one. What is this line for? Yeah, okay. So I want to plot the reference on the scope. And so this is the result. The reference line, purple. The actual spacing is the black one. So it eventually can catch up to the desired distance after some 200 seconds in this case. Quite long, because I'm using the um, unmeasured value of C. The C is the variable depending on the friction. Yeah, that problem is too high, so it makes the whole system to react slower. Okay, and then you can actually adjust the response time of the controller in the MATLAB. You can tune the PID control here to match with your desirable response. Okay, so I have no time to play with it. Maybe you have more time than me. You can try, or you don't have time at all. Okay. Any question on the example? So basically, after you graduate from this class, not from the school, yeah, not from the SU, just from this class, you can make your car to be a cruise control car. If you plant the correct system on your car, you can make it a cruise control system car, following the lead car with a certain spacing. You can experiment on that. Experiment on the lab. Don't try on highway first. No, no, no. That's dangerous. Try use the small system using Tamiya, let's say, or Plarail. You know Plarail? Yeah, small train system. You can use that for experiment. Okay. Any question? No. All right. This is the notes that I gave you last week also. Yeah, that I'm saying to you that the focus on the control system design is not on finding this time domain response. That's not the focus, although you need to be able to do that. Yeah, that is a must, but that's not the focus. The focus is here. Yeah, the focus is you want to design the controller so that this whole system achieve this. The first thing is to stabilize the system. Yeah, most control system is designed to be stable, and then you want to regulate the output. You want it to be equal to the desired output, and then achieving some time domain measures. What are those? The response time, overshoot, settling time, right? And then you want to reject disturbance. Yeah, your system might be subject to some disturbance like wind disturbance. Yeah, and another thing that you might not know is that when you are applying your control system, the mass of the car is unknown actually. Yeah, you cannot limit the car. I set the controller when I designed the controller when I set the mass to be 1,000 kilogram. If it is more than that, no, it won't work. So we have to reduce the mass, add the mass, it 1,000, no, it doesn't work like that, okay? There are 2% inside, 3% inside, the car is full, the car is empty, your controller must work, okay? So in face all of those disturbances, uncertainty, your controller must also work. Yep. And then number 5, this is an advanced version because we are not going to teach you on this constraint control system. Although this is a real world case, but we are not reaching that level yet in this class. Okay, this is what I meant by number 3, time domain measures. Okay, and this is how you achieve the time domain measures. Yeah, the TS 2% and 5% is governed by the 4 divided by sigma. What is sigma? Sigma is here, zeta times omega n. And also the maximum overshoot in percentage depends on the sigma and omega d. Omega d is what? This is omega d, yeah? Omega n times this one is the square root. So you see all of these time domain measures depends on what? Only 2 parameters? Yeah, correct. Only those 2 parameters. So you design a controller, get the correct omega n, get the correct damping ratio, you will get the desired characteristics. Okay, that's the whole point. Any questions so far? Yeah, let's move on. So in simple terms, I mean mathematically. What I mean by simple terms is mathematically, you are to design mn a1 up to am plus 1. Yeah, all of these parameters. Yeah, s to the power of m. This is s to the power of n. So that all of these are achieved. Yeah. What does it mean by determining m and n? That is to determine the order of the control. Is it first order controller, second order controller, third order, or zero order? Zero order means proportional controller. Okay? Yeah, jadi
Is M always more than
at least equal to n. For physical real system, at least equal to n. No, no, no. For it to be realizable, so that you can realize the controller, it has to be at least the same with n. But in this class, when you are designing the controller, theoretically, you can make m to be greater. It is okay for the class, yeah. For the sake of the class, it's okay. But in reality, we cannot realize that. MATLAB will also accept that. Yeah, you set m greater than n, you input it into MATLAB, MATLAB say error. Yes?
ideally M should be bigger than
M should be smaller than n.
M. M should be smaller.
Yeah, yeah. So the ideal controller looks like this. Let's say Ks is A over S plus B lah. So the power of M is 0. Yeah, and here this is 1. In this case, M is 0, N is 1. So this is good. What's bad is, or non-realizable is, if you have, let's say, AS over B. Now, we cannot realize this in the real life, but in exam, you can do this, okay? Or KS equal to A plus S over B. Things like this, you can do this in exam. Okay. So an example, what about this? Can you stabilize the plant? First question, is this stable? 1 over 6S, is this stable? What's the requirement for BIBO stability? The pole should be, the real part of the pole should be negative. So what is the pole? Yeah, the pole is 0. Yeah. So is it negative if it is 0? So is, yeah, it is neutrally stable. So not bibostable. Not bibostable. So can you think of an idea? Choose A1, A2, B1, B2 to stabilize this. What's your approach in this? Any idea what's your approach, Reza? We cannot do that directly. Okay, correct. So the first step is to make the closed loop transfer function. Yeah, is, yeah, multiply it first, and then we make the closed loop transfer function. Okay, so let's say we have the two objectives. Yeah, the first one is to stabilize the plant, and the second objective that I said, we want to get omega n 4 radian per second. Let us do the first step. So the first step is always to get the closed loop transfer function. So this is the closed loop transfer function. So only from here you can check what is the A1, A2, B1, B2 needed to stabilize it. Yeah, you can see it from this. Okay. So what's your idea? How to stabilize the closed loop transfer function? What's A1, A2, B1, B2 that we have to choose? You can choose any number. Oh, I10. Yeah, good idea. What else? So Nathan said A1, we make it 0. S is gone. Okay, that's good idea. Okay. What else? Yeah, bibostable. We only need bibostable. Denominator into what? This is what is the question and what? Yes, that one can. Also you can do that. Yeah. Any other simpler idea? B1 you make it -1. Come on, think. Alfie, Anissa, no idea. We only want to make the pole to be stable. Yeah, negative real part of the pole. Make B1 bigger than B2. A bit complicated. Yeah, Nathan did the first part. There is a second part to it. A1 0. Nah, A2 0 cannot. No, you make B1 0.
Oh. Yeah.
It doesn't have to be second order system, right? We only need to make it stable, just stable. Although you can also do that, yeah, B1 or 0, you can also do that. But this is the simpler part. So you see, A10, B10, this is the final closed loop transfer function. So the pole is at this, yeah. So for any what? For any,
For any
yeah, we want, what we want to say is that for any A2, B2, but what does A2, B2 require? What is the requirement for A2 and B2? Which part is positive? A2 positive, B2 positive, or what?
yeah.
No, no, no. The this one, as long as this is positive,
Oh yeah.
then your pole will be negative. Okay, so you can make A2 minus negative, B2 negative. You can do that, right? Yeah. Yeah, the pole is just this, the bottom part.
Bottomnya aja.
So is S in the bottom.
S is the.
As equal to negative.
Okay, let us review on how to get the pole. Yeah.
You're solving for S.
Yeah, you're solving for S.
You're solving for S.
Find the root of S.
Kan S dengan B2 plus R2 minus 0.
Okay, hold on. Now let us review on how to get the pole. Okay, so the GCL of S is A2, what? S6
Plus A2.
plus A2. Okay, pole is defined as S that makes denominator to be 0. Okay, so how you do it? You create an equation which states that S6B2 plus A2 is equal to 0. And then find S that satisfy this. Okay, so S6B2, and so that's it.
Kalau polnya.
Any question up to this part? This will surely appear in the exam. Say that again.
If it's 0, it's neutrally stable.
If A2 0, neutrally stable. What if B2 0? We cannot make B2 0. B2 0 means your K is infinite. We cannot make infinite K. Infinity is you know, exclusive for Nissan. Nissan. You know what I mean? Yeah. Okay. Now, how do we get the 4 radian per second? Alfie, any idea? What?
Formula. 6B2 plus A1 equals to omega L. A2 equals to A2 square equals to 4.
Say that again. Which one?
A2 square equals to 4.
A2 square.
A2 equals to
4 square.
4 square.
That's correct. But that's not correct also.
Basically, we turn the
Correct.
pole,
Correct.
we turn the pole into the
Yeah, remember this basic formula, yeah. The top part can be anything, okay, but the bottom part, it has to be S square to,
delta omega S plus omega N squared.
okay. So the multiplier here must be 1. Make it 1. So how do we make it 1? Yeah, we divide by 6b1. Okay. So omega n square will be A2 over 6B1. What about A1? Do we need A1 here? Do we still need A1 to make omega n 4 radian per second?
Yeah, if it's zero, we can just make it.
Yep. So we cannot achieve the omega n 4 radian per second with this controller, yeah, A2 and B2 only. That is for sure. So we can do this, yeah. We divide, just like we said, divide by 6B1. This is the result. Okay. Divide all of the terms by 6B1, and this is equal to omega n squared. A2 over 6B1 is equal to omega n squared. Yeah. So the first conclusion, A1 0 is okay. Yeah, we don't need A1. And then, yeah, see this? And so we get A2 equal to 96 of B1. Okay, what's B1 that we need and A2 that we need in this case? Huh?
That A2 equals to B1 equals to 1.
Yeah, you can do that.
A2 over B1 equals A2 over B1.
Yeah, so Nathan said B1 equal to 1, A2 equal to 96. That's fine also. You can get stopping you from that number. Yeah, it will affect this one. Yeah, you see the choice of A2 and B1. This is B1 is over here. Yeah, so let's say your choice of B1 is 1. A2 is going to affect your natural frequency, yeah? But then B1 here is going to affect your damping ratio. So that, yeah, so you have to think about both. If in this case, you only need to get the 4 radian per second, damping ratio is free, yeah? Then you can set B1 free also. Yeah, unless the problem states you have to get omega n this radian per second, zeta this much, then you have to think of all of the parameters. Okay. You have to think about the customer, what the customer wants from your system. Okay. Yeah.
So we have a derivative, we can send B1 1.
Yep. So this is binded, and then B2 is going to affect the zeta in that case. Yeah. So from the equation that we have there, you have 6 B2 plus A1 over 6 B1 also, yeah. This is equal to 2 zeta omega n. Okay. So because you set A2 equal to 96 B1, so you set it there, and then 6 B2 plus 96 B1 over 6.
That's A1, sir. So therefore, we said
Oh, sorry.
B1 is not.
This is 0, yeah. A1 is 0, right?
Yeah, A1 is 0.
Oh, okay. Oh, okay. I forget. A1 is 0. Okay. This is A1, so this is 0. 6 B1. So B1 is equal to,
Over 6.
yeah, so this is 6 times, yep. So we have set the value of A2 to get the 4 radian per second, and then your zeta depends on the B2 in this case. Okay. Is this clear? Yeah, you just have to match the number lah. Match the number. So
So zeta can also be
zeta,
B1 is very small.
no. Once you set A2 and B1 in this fashion, the zeta dependent on the B2 in this case. Okay, because this number is defined already. Okay, the bottom part defined already. So your zeta dependent on the B2 in this case. Okay.
Again, it's support.
Hmm?
So second order function, order function is not only on the plan, but the combination of the plan and the control.
Yeah, of course. Your system originally is first order, right? 1/6s, first order. So once you combine with the controller of which part? Where's the controller? Yeah, this controller, then the system becomes second order system. Okay. And when you are asked about finding the omega and 4 radian per second, that is for the closed loop system, not for the open loop system. Okay. Yeah.
How do we get from part of the system?
This one? No, that's separate problem. You see, previously we discussed only to stabilize the plan. Stabilizing the plan, we say we only need A2 and B2 to be there. Yeah, we don't need A1 and B1, which is why we only need this controller. I mean, we only need to get to this transfer function.
That means that if you want the plan to be always stabilized, we can use the control system.
Yeah.
And then but if we want to have omega n and we want to get the mid
Damping ratio.
we need to expand the
Yeah. So let us conclude here. Yeah, if you want to stabilize, then your controller is just A2 over B2. Okay. If you want to stabilize and you have 4 radian per second, then your K of S should be on the form of A1 is still 0. Okay. A2 over B1S plus B2. Okay. Chris, it is okay, Chris? Oh, not okay? Yeah. Alfie, this is okay? Okay. Right. So I want you to do this on your paper. Yeah, do this on your paper. Your job is to choose the remaining parameter, yeah. So that the TS 5% is 10 seconds. Okay, one group, one answer, so that you can discuss with your group.
So what do we choose? The B2 and B1. Yes, so the parameter that we choose B2 and B1.
A2, B1, and B2.
B1 is B2.
A2 is
Which one?
A1 is 0.
A1 is 0, but A2 must be this with B1. Okay. Now we are continuing the previous problem. Okay. So A2 must be this.
So we use that function, right?
Use this function.
I mean the GS.
The GS is this. Yes. Find. You have to find A2, B1, and B2.
A2, B1, B2.
Okay, ya. Target omega n 4 radian per second, and then settling time 10 seconds. Find A2, B1,
Ini
B2.
jauh-jauh kali. Sama slipper. Oh iya.
So what's your approach?
We find the Z of
Ini
like it into the
Yeah, okay.
Kan dapat 96B1 per 6B1 sama dengan omega X2.
What is the required zeta for this case? Huh? No, the required zeta. Now you see, omega n is 4 radian per second. We are continuing the previous. Now, this relationship saying that omega n is 4. Yeah.
kayak 3 ya.
What do you get? I'm still writing the problem. Which one?
3/40.
What's your step? Let me get your step first. Your first step is what?
So we
You compute the what? What value?
this one ignores. So we start from here.
2 zeta omega n.
Yes, from the standard form.
Okay.
Terus kan we know the WN, right, which is 4.
Okay.
So sigma is equals to 4 zeta.
Yes.
And we plug it into the TS 5%.
Okay.
So 3/4.
Then you get the zeta.
Yeah.
Yeah. Okay. That's correct. That's how you get the zeta. And then after that you get the zeta. You have to get A2, B1, and B2. Okay. But you get the correct first step. Okay.
So this is the function.
Okay.
I input this value and then it becomes this. I said B1.
You said B1 to B1, A2 to B.
96.
Okay. So it becomes 16.
Yeah.
Yeah. So omega n is 4. Okay. Okay. And then
Zeta, calculated zeta to be 13.3.
Ah?
0.3.
no zeta 13.
nggak boleh. TS 5%-nya harus ini.
Ya TS 5% kan?
TS 5% is 10.
Ya. The
3 over
Wait,
sigma.
3 over sigma.
3 over sigma is 10.
Omega n kali zeta.
Yeah, is equal to
Sama dengan
10. Yes. Omega n is 4, right?
3, 4.
What is zeta? So you zeta go here, 10 go there. So 3 over 40. zeta is 3 over 40. Yeah.
B2 over B1 is 0.3.
How do you get that?
Does this work?
I don't want the answer. I want the method. What's the method?
So first, we already know that
No, your method.
omega n squared is 4. F16. So omega n is 4.
Yeah, then
And then we can get the zeta from TS 5%. We can get the sigma first.
yeah, get sigma first, and then you get the zeta. Yeah, what's the zeta you get?
Zeta is 0.3 over 4.
Okay, and then after that you get the zeta.
After getting zeta, we can search for the value of B2 over B1.
Okay, that's correct.
0.3.
Okay. So that's how you get it. What is the value of A2 you choose? What's A2?
A2, A2 I substitute with
Oh yeah. You haven't set you haven't chosen any number, but you just compute the ratio of those numbers. Yeah. Now try to get the number.
and Z.
Does
Wait,
this
wait,
ratio
wait.
suffice? Just this ratio.
No, if you are asked to design the controller, then you have to choose the number exactly.
Wait, this can be 3, this can be 5.
But 96, what A2 is 96 B1? Oh, for 80s. Okay, I misread it. Yeah,
We get when first we find zeta.
yeah. Okay,
The relation B2 and B1 is equal to 2 zeta.
correct.
Correct, right?
Mm,
Then we can just make the ratio of B2 and B1 is 3 over 5.
okay, that's correct. Yeah.
It's too much, bro.
Zetanya 0.075
Wait.
and B2-nya 0.
Zeta berapa?
0,075.
It's 3
Oh,
over 5.
okay. Yeah, 3 over 40, and then
B2-nya 0.6.
B2 0.6. What's B1? Oh, you choose B1 is this. Ah, okay. Yeah. That's correct. Okay. You get it?
Still figure
This,
that.
your same group.
Pi zeta omega L probability B1 zeta 0.
Bisa kita coret.
Okay. Yeah.
This 6 over 10 to this.
Yes. So you can pick any number. So those number ratio are correct. Yeah. Okay. Yeah. Mm-hmm. Okay. What else? You want to ask?
So the question is, we use all the transformation with the omega, and then we less surface.
Say it again.
What I think is we equalize this and this, so we make this equal to this and then find the number, isn't it?
Yeah, correct. Yeah. So it's like B2 over B1 is 2 zeta omega n. Yeah. And
What's
then
the S?
hmm?
Then what's the S?
S is the Laplace operator.
We leave it
We leave it there. We leave it there like
just S.
t, right?
Just a variable.
It's a variable. Anyone else? Your group? You get the zeta first?
Yeah, my zeta is
Is this one? Okay, and then after that,
using the second order equation,
okay,
and B2 and A2 relationship using the second order also.
okay.
This one.
B2. Okay. Yeah. Choose a number. You haven't chosen a number yet.
Any number? What number is it?
Any number.
Any number, yeah.
Any number you can do. When you are designing a controller, you have to define what is the A2, B1, B2. Although the ratio, you are only computing the ratio now, right? But you haven't picked the number exactly which number to choose.
For which one should I substitute?
Up to you. You can start with any number. Let's say you start with B1. B1 equal to 1. Let's say.
Then try to find the others.
Yes. Okay. I think all of you get it correctly already. Your part, your group not yet. Okay, let us recap here. So all group, so Reza, we can see it first. Then we can have another example after this. So to recap, you know that omega n 4 is required, and then yeah, it is given. TS 5%. This is 10 seconds, and this is equal to 3 over sigma. So that is 3 over zeta times omega n, which is 3 divided by zeta times 4. So from here, you know that the zeta is 3 over 40, which is 0.075. Okay. And then we know that the B2 over B1 is the 2 zeta omega n. Yeah. So this is equal to 2 times 4, which is how much? 0.6. Okay. So now we know that B2 is 0.6 B1, and then A2 is 96 B1. So what number to choose? We can choose B1 equal to 1, and after that we compute the rest. Yeah, if B1 is 1, then 0.6. This one can do. If we choose B1 equal to 10, what happened? 960. Huh? 6. Okay. Yeah, B1 any number. In yeah. You compute. Yeah, any number can.
Any number, as long as you complete the number.
Okay, you choose B1 first, and then compute A2, compute B2.
As long as the ratio.
Yeah, this ratio the same. Okay, that's it. So if the controller can be any of this number, what's the point, right? He said, what's the point? Reza said, what's the point? What's the difference between this? Yeah. No. Yeah, B1 and 571 you can. Because the target is only these two. If you have other target, then this number may not be free to choose. Yeah. What's the example? Or let's say, what is the effect of choosing different B1? What is the effect?
This case, nothing. The WN will be the same.
Omega the same, zeta the same. So the difference will be in what? There will be difference. There will be. So what it is?
Here, the computing hardware.
Huh?
The hardware of the controller.
Hardware or controller? What else? What's the difference? No, overshoot the same.
Like the steady state, I mean.
Okay. He said steady state value. Steady state value will be different. Okay. You see, steady state value will be determined by this.
Oh,
You keep increasing the value, you get.
So it does.
Oh, sorry. It's the same, yeah. Sorry. I beg your pardon. It's the same, yeah. It's the same.
So it does not change the
What is the KS here? It's A2 over B1S plus B2. Okay. And so if we return back to the original system, what happened? Wait. The closed loop system will be what I say. So it's A2 divided by S square 6B1 plus what is it? Let us just see. Yes. Oh yeah, S 6 B2 plus A2. Okay. So it's A2 over A2. Yeah, nothing happened. That's true. Nothing will happen with the steady state value. Steady state value is still the same. Yeah. Okay. So let us conclude here. Yeah. No matter what your A2, B1, and B2, your steady state value will be the same because it is just governed by A2 over A2. Okay.
All the same lesson. And the value is also the same.
Yeah, it will be the same. Just happen like this. Okay. But for other system, it might not be the case. So you have to check the final value theorem. Yeah. Okay. 28, I2, 96 of S plus. Yeah, but then if you compare 96 over S plus 0.6, you compare with 10S plus 6. Yeah, nothing changed.
And the properties.
Yeah, the control properties are still the same. They still have the same pole, controller pole are the same. So controller response are the same. So these are just numbers where you put there, the controller become the same controller. Okay. Yeah, even the if you put a step input to the controller, the final value is still the same. So nothing changed. Yeah, beautifully for this case, I made any number you put here will result in the same controller. Okay. But for other controller, for other system, this is not necessarily the case. Okay, so you have to check. Okay, what about this? Let us read the problem together. This is the open loop transfer function. Okay, and then you are asked to obtain rise time, peak time, maximum overshoot of the closed loop system with unit step input. With unit step. How does it look like? When you draw the problem in a block diagram, how does it look like?
1 over S plus 1.
And then like this.
Yes.
Let's say that's the CS, this is the R. And then what is RS here? Just 1 over S. So you find out the rise time, peak time, and overshoot of the CT. Yeah. The CT is going to be like this. Okay, that's the CT. So you find out what is the rise time, peak time, maximum overshoot. What's the first step? Okay, make closed loop. Okay, Reza, your group, can your group do this? Your chance now. This is your chance. No, come on. Make the closed loop transfer function. It says unit feedback input. Unit step input. Yeah, unit step is 1 over S. One over what? Yeah, where's the H you mean? Yes, and then? Yeah, but H is 1 in this case. H is 1. Yeah? Sorry. Say that again. You find the closed loop first. Yeah. Yeah. Okay, get the closed loop 1 over S square plus S. Not S square plus 1, S square plus S. Divided by 1 plus, no, don't do that. 1 over S square plus S divided by 1 plus yes, that S square plus S plus 1. Oh, you want to do that? Okay. Step by step. S square plus S plus 1 divided by, okay. Yep. Okay. And then that's the closed loop transfer function, right? You need to find the rise time, peak time, and maximum overshoot. No? Why? Yeah.
Ini kalau misalnya ada hitcher,
Then you multiply with, if this is your G, this is H, like this. This is your question, right? And then your closed loop transfer function is G over 1 plus GH. No, plus. So if this is minus plus, then this is plus minus. If this is minus, this is plus. If this is plus, this is minus. You get it? Are you going to find C? Are you going to find the CT, which is Laplace inverse of CS? Are you finding this? No need, right? So we don't need Laplace table in this case. So how do we do this? Yeah? No. Yes, closed loop, okay. Okay. This one. Yes. That's it. You multiply 1 over S. No need to do that. So once you get the closed loop transfer function, find out the omega n, find out zeta, and compute this. Peak time TP, peak time TP, rise time TR, maximum overshoot MP percent.
I have good value for omega n.
Hah?
Bisa plus minus kan? Plus minus kan di atas kan?
What?
So frekuensi mana beda?
Oh iya. Nggak ada plus. Jadi plus plus.
You got a plus lah.
Agar one is plus minus one.
Yes, plus minus one, but we take the positive value, of course.
Frekuensi negatif. Kalau frekuensinya negatif, lanjut negatif.
Ini dari
Kontak tadi.
How is it, Reza? Do you get it?
haven't.
Oh, okay. So omega n is what's omega n? 1. Okay, two zeta. So zeta is 0.5. Okay, correct. Ya.
Belum, betanya belum saya.
Beta. You find beta.
Beta dulu, beta.
Yeah, just now I saw some group open Laplace table. No need to open Laplace table in this case.
60. Ya, sama. Beta 60. Ya, beta 60. Saya sama. 60 degree ya? Ya, 60 degree. Degree. Gantian. Berarti ya, balik.
In this case, this radian, not degree. Beta is radian.
Ya, equals to 5 minus 4 Mas. Ya, terapi. Bro, akar bro.
Done already? Settling time, yeah, which one? 2 or 5. If it is not defined, you can choose. Finish, okay.
What is overshoot?
Man, which one is about? It's okay. Whichever is fine. The settling time, whichever is fine. How do you get this 0.16? Calculator. What's the overshoot you get? 16%. Okay. Yeah. So 0.16 that you get is not in percent yet, but you want to get in percent times 100%. So 16%. Okay, let us conclude this problem. Okay. First step, find the closed loop transfer function. That is okay, this one. And then get the omega n, zeta. After that, you get sigma, omega d, and then beta. Okay. So based on this value, you compute all of those time, rise time, peak time, setting time using this, the red one, yeah. Yeah, it will be given. Okay. So students, in percentage, this is 16%. But what is the value of MP as a value, not in percentage?
16% of the steady state.
Okay, how do we get it?
Use Pythagorean theorem times
Yes.
0.6 persentasenya bagi 16 kali 116. Steady state value kita nggak tahu. Kali 100.
So if you want to answer what is the maximum overshoot, you have to find out the limit t go to infinity of c of t first, okay, which is s0 s times 1 over s, okay, yeah, which is equal to 1. So MP in that case is 1.16. Sorry, 0.16. No, MP is just this. This is MP. MP is this one, yeah. So MP is 0.16.
Oh, isn't it? Oh, I thought 60% dari bawah. Bukan 60%, 0.60. Not that like that. Start from 0.
No, MP is this. It's from the steady state to the peak.
Oh, I understand.
Okay.
MP is steady state.
Let us continue.
Oh, I understand.
Still any question on this? Any question on this? Okay, clear? What about this?
It's already close to 0.
What's the idea here? Just tell me the idea. We are running out of time.
We trace back. Make close loop.
Sigma
Oh, that was good.
from the 2% we get sigma equal to 2.
That's
Then
right.
put the beta omega there. Yeah. So yes, from the sigma.
From the MP, we can get the relation between sigma and WD.
Okay.
We can get the sigma from the TS 2%.
Yeah.
Okay.
We get the WD.
Yes.
We get WD, we can get N.
Yeah. This is where you use the natural log.
Yeah.
Use the natural log in here. Okay.
Okay.
Yes, correct. You trace it back. You get the idea lah. Clear on this? So easy, right?
Log-lognya tolong ada kasih Gaussian comparison. Yeah.
What?
Gaussian comparison.
You can use the calculator, right?
It's LN, no?
LN. Kan kalau if it's E,
So how to do this? 5%, right? So 0.05 is equal to e to the power of zeta omega d times pi. So you take the natural log on left and right. Yeah.
Oh, even
LN.
It's just ln of e.
Oh,
half pi, like this, right? So this moves down.
Yeah.
Okay, you can get this from calculator,
Yeah.
and then in here become minus
Oh.
pi times ln of e. Okay, this one 1, right? This is negative 3. So the number becomes positive, then you get. So you can get relationship between zeta and omega d. Okay, next problem. Get me the idea. What's the idea? Read it first.
The main value of AB, you just ignore A.
Yeah, simplify the
A is trapped.
No, you need the A so that you can get the unit step response. You need to compare. But let's say you want to get the KH only. What's the idea?
Simplify both.
Huh? Simplify, okay. Then get the closed loop transfer function.
yeah. We get the damping ratio, we get the natural frequency,
Yep.
find the relation between the
Yep.
expanded simplified transfer function
Okay.
with the damping ratio and the natural frequency.
Yes. So that's the idea, yeah. So in the formulation of the damping ratio, you will have the KH in the formulation so that you can compute what's KH. What about the omega n? Omega n, you keep it the same 3.16. Okay, in this case. What about this? What's the idea? Cost loop first, okay. Okay. Expand into the 2 zeta omega n and then omega n square, okay.
Everything else and calculate.
Yeah, okay. So because we only have one variable in here, you make zeta to be 0.5. Can you determine the omega n independently? Let's say you have set the k so that zeta is 0.5. Can you again adjust the omega n after that? You cannot adjust omega n, yeah, because k is set to adjust the zeta. After you get that, omega n is dependent on the k. Yeah, dependent on k. Yes. Once you get the omega n and the zeta, you compute this all using the formula. The rest is just using the formula. Okay. So the key thing is getting closed loop transfer function first, and then expand in the second order system format. This one, I think I still have, but they are the same type of problem, which will appear in the exam also. Okay. So I will see you again on next Monday. Yeah.